into video, just like that. Let's meet Goku. Unlike standard diffusion models, Goku uses rectified flow transformers, a smoother, more direct way to learn how to transform noise into realistic images and videos, leading to faster training and sharper results. At its core is a 3D image video VAE, compressing both images and videos into a shared latent space, meaning Goku doesn't treat video as just a stack of frames, it actually understands motion. It also ditches patchy temporal attention in favor of full attention mechanisms, so videos stay sharp, fluid, and consistent. With 160 million images and 36 million videos, Goku just scored 84.85 on VBench, outpacing the top video gen models. So how does rectified flow make this magic happen? Let's dive in.
Goku is a new family of models designed for both image and video generation. The core idea? They use something called rectified flow transformers, which are meant to push the boundaries of visual generation. No figures or equations here yet, just a high-level overview. The abstract lays out 4 key ingredients that make Goku work: a data pipeline, model architecture, flow-based formulation, and large-scale training infrastructure. These elements allow Goku to set new records across several benchmarks. For example, it scores 0.76 on Generative, 83.65 on DPG bench for text-to-image generation, and 84.85 on VBench for text-to-video. Numbers like these suggest that the model is performing at the cutting edge. Moving into the introduction, the paper frames video generation as a rapidly growing field, with applications in media, gaming, and AI simulations. It highlights key advancements that have made modern video generation possible: improvements in generative models, larger datasets from the internet, and increased computing power. Then comes the main focus. Goku is a family of rectified, flow-based transformers built for both image and video generation. Unlike other models that specialize in just one, Goku aims to handle both effectively. The authors break down its design into 4 parts: data curation, model structure, flow formulation, and training efficiency. These aspects will be covered in detail later. So that's the first page in a nutshell: a high-level introduction to the model, why it matters, and what's coming next. Now let's get into what Goku can actually generate. If you look at Figure 1, you'll see it's packed with examples of text-to-image and text-to-video outputs. The text-to-image section has some visually striking generations, like a Bengal cat with tribal accessories or a futuristic-looking GOKU logo. The text-to-video samples are even more interesting because they show continuity between frames, meaning the model isn't just making isolated images, but stitching them together in a way that looks natural. Next, the paper explains how they built the massive dataset that trains these models. They don't just scrape random images and videos, they filter them rigorously using a combination of aesthetic scoring to ensure visual quality, OCR-based content analysis to make sure the images actually align with their captions, and subjective evaluations to double-check that everything makes sense. They also bring in large language models, or MLLMs, to generate detailed and contextually relevant captions. But they don't stop there. They refine these captions using a second language model to improve fluency and clarity. The result? A huge dataset of 160 million image text pairs and 36 million video text pairs. Finally, they introduce something called rectified flow formulation, which is the backbone of the Goku models. This approach is designed to improve how images and videos are generated together, and we'll see more details about it later. So this page does 3 things. It shows off Goku's output, explains how they built a high-quality dataset, and teases the rectified flow technique that powers the model. Let's talk about the core architecture and training setup of Goku. First, it uses a 3D joint image video variational autoencoder, or VAE, to process both images and videos in a shared latent space. In simpler terms, instead of treating images and videos separately, it compresses them into a common representation, making training smoother and ensuring better alignment between frames. On top of that, it integrates a full attention mechanism, which likely refers to transformers helping to maintain coherence across images and videos. Then, the paper shifts to the training infrastructure. Goku is built to scale, so they've optimized the entire training pipeline using 3 key techniques: parallelism strategies to efficiently manage memory when training on long sequences, byte checkpoint, a high-performance system for storing model states efficiently, and fault-tolerant mechanisms from Megascale, which help ensure that large-scale GPU training runs smoothly without crashes. After explaining the training setup, the page moves to benchmark results. Goku achieves state-of-the-art performance in both text-to-image and text-to-video tasks. It performs exceptionally well on standard benchmarks like Text-to-Image Comp Bench, GenEvil, and DPG Bench for text-to-image. And it dominates UCF 101 and VBench for text-to-video. The numbers from earlier pages make another appearance here. Goku scores 84.85 on VBench, placing it at the top of the leaderboard as of early 2025. Finally, the next section introduces the three main building blocks of Goku. The image-video joint VAE, which compresses visual data, the Goku transformer architecture, which generates images and videos, and the rectified flow formulation, which improves motion consistency in video generation. The rest of the paper will expand on these, but this page sets up the big picture. Goku isn't just another generative model. It's built from the ground up to handle both images and videos together, trained at a massive scale, and designed to perform exceptionally well in competitive benchmarks. Now let's take a closer look at Goku's transformer architecture. If you glance at Table 1, you'll see different model configurations. There are 3 sizes, 1 billion, 2 billion, and 8 billion parameters, with increasing complexity in terms of layers, dimensions, and attention heads. The smallest model is mainly used for testing before scaling up to the larger ones. Then, we get into the design of the transformer block. Goku builds on Gentron, a diffusion-based transformer designed for text-to-image and text-to-video tasks. The architecture has multiple key components: a self-attention module, which captures relationships between different tokens, a cross-attention layer, which injects textual embeddings from a language model, a feed-forward network, which refines and projects features, and an adaptive normalization block, which incorporates time-step information to guide feature transformations. The page also talks about 3 key optimizations. First, full attention. Instead of separating spatial and temporal attention, Goku unifies attention across both images and videos, which improves motion modeling. It also uses flash attention, a memory-efficient method to handle long video sequences efficiently. Next, patch and pack. This is a packing strategy inspired by Navi-T, which allows images and videos of different resolutions to be batched together, avoiding wasted computation. Finally, 3D rotary position embeddings. This is a technique that extends the idea of relative positional encoding to 3 dimensions. It helps the model generalize better to different resolutions by handling both spatial and temporal variations effectively. So, the big takeaways? Goku's architecture builds on existing transformer models, but introduces several optimizations for efficient large-scale training and better handling of both images and videos. This page covers 2 big ideas: stabilizing transformer training and flow-based learning for generating images and videos. First, let's talk about training stability. Large transformer models often run into a problem where training gets unstable, leading to loss spikes. Basically, sudden jumps in error that can ruin the model. This can cause the output to be garbled or noisy instead of realistic. To fix this, they use query key normalization, a technique that stabilizes the attention mechanism. Specifically, they apply RMS normalization, which smooths out the feature representations before attention is computed. This ensures that training remains stable and reliable. Now, onto the flow-based training method. Instead of jumping directly from noise to a final image like traditional generative models, Goku uses a gradual transformation process. Imagine blending 2 images. One is pure random noise, and the other is a real training example. The model slowly morphs the noise into a structured image by learning an interpolation process that progressively shifts the sample toward reality. This method, known as rectified flow, has some serious advantages. It simplifies the model structure, making training faster and more stable. The team ran a test on ImageNet-1K, using a small Goku model with 28 layers and 16 attention heads. The results? Goku, with rectified flow, converged in 400K steps, whereas traditional diffusion models needed over 1 million steps to reach the same quality. In short, this page explains why Goku trains efficiently and reliably. It avoids common pitfalls in transformer training and introduces a faster alternative to standard generative approaches. This page focuses on training efficiency and how Goku is optimized for joint, image, and video learning. If you look at Table 2, you'll see a comparison between rectified flow and DDPM on ImageNet. The key takeaway? Rectified flow converges way faster. It reaches competitive performance in just 400K steps, while DDPM needs 1 million steps to get similar results. That means training a model with rectified flow saves time and computation. Next, we get into multi-stage training, which is designed to help Goku handle both images and videos at the same time. Training a model for just images is one thing, but videos introduce motion and temporal dependencies, making it way more complex. To make this work, the authors break training into 3 stages. The first stage is text semantic pairing, where Goku is trained to match text prompts with images. This helps it learn the basic structure of objects, spatial arrangements, and attributes before moving on to videos. The second stage is image and video joint learning. Here's where things get interesting. Instead of training images and videos separately, Goku learns both together using a unified transformer framework. Since high-quality video data is harder to collect than images, they use images to boost video training, making sure video frames are consistent and visually sharp. The third stage is modality-specific fine-tuning. The last stage fine-tunes the model separately for images and videos. For images, the focus is on making them sharper and more realistic. For videos, the priority is smooth motion and stable frames, so the model doesn't generate flickering or inconsistent movement. Finally, they introduce cascaded resolution training, which is a clever trick to gradually increase resolution during training. The idea is to start with low-resolution images and videos, 288 × 512, so the model can focus on basic relationships. Once that's stable, they increase resolution step by step, going from 480 × 864 to 720 × 1280. This helps the model adapt naturally without overwhelming it with high-res details too early. In short, this page is all about efficiency, both in how the model trains faster than DDPM and how it progressively learns from text to images to videos, refining quality at each step. This page covers how Goku extends from images to videos and how the infrastructure is optimized for large-scale training. First, let's talk about image-to-video generation. The model takes the first frame of a video clip as a reference and uses it as a guiding condition for the rest of the video. This is a common strategy in video generation, since it helps maintain visual consistency across frames. Essentially, Goku takes that reference frame and broadcasts it across all video frames, making sure that the generated frames remain aligned. To refine this further, they add a single-layer neural network that helps adjust the channel dimensions to match the model's structure. Then, we move into infrastructure optimizations, which are crucial for handling massive models like Goku. The authors introduce several techniques to make training more scalable and efficient. The first strategy is parallelization, which is necessary because Goku has an extremely long sequence length, over 220K tokens. To manage this, they use a 3D parallelism approach, splitting the workload across 3 axes: input sequences, data, and model parameters. Now, let's break down 2 key parallelism strategies. The first is sequence parallelism, which slices input sequences into smaller chunks, reducing redundant computation and memory use. It helps speed up training while maintaining accuracy. Goku uses Ulysses, a system that ensures smooth sharding of sequences and efficient attention computations. The second is fully sharded data parallelism, which distributes parameters and optimizer states across multiple GPUs, reducing memory bottlenecks. Instead of having every GPU store a full copy of the model, they shard the parameters and only gather them when needed. The approach minimizes communication overhead and speeds up training. So in simple terms, this page explains how Goku extends image generation into video while maintaining coherence, and then shifts to how they ensure the massive model trains efficiently without hitting memory limits. This page focuses on training efficiency and fault tolerance, essentially, how Goku handles large-scale computations without breaking down. First, we have activation checkpointing. Training a massive model like Goku means handling long sequences, which can quickly overload memory. To deal with this, they use a technique called fine-grained activation checkpointing. Instead of storing activations for every single layer, they selectively save only the necessary ones, reducing memory usage while keeping training efficient. This lets them balance computation and communication, ensuring that GPU resources are used optimally. Next, we get into fault tolerance. When training across thousands of GPUs, failure is inevitable, whether it's a hardware issue, a crashed node, or a power failure. To prevent wasted computation time, Goku uses a system called Megascale, which includes self-diagnosis, monitoring, and fast recovery mechanisms. This means that if a node fails, the system automatically detects it, fixes it, and resumes training without major delays. Then, we have saving and loading training states. When training a model of this scale, checkpoints are crucial. They store model weights, optimizer states, and other key parameters. This helps ensure that training can resume smoothly, even after an unexpected interruption. They use Byte Checkpoint, which is designed to handle parallel saving and loading of model states across multiple GPUs. The efficiency here is impressive. Checkpointing a massive 8B parameter model across thousands of GPUs takes less than 4 seconds. That's incredibly fast compared to the overall compute time per iteration. Finally, we get into data curation. The Goku model relies on a huge dataset for training, consisting of 160 million image text pairs and 36 million video text pairs. This dataset is collected from public academic repositories, internet sources, and proprietary datasets from research partnerships. They also perform extensive filtering and processing to make sure the dataset meets high-quality standards. So, in short, this page is about making large-scale training work smoothly. The authors tackle memory efficiency, GPU failure recovery, checkpointing speed, and data quality, all crucial for ensuring Goku trains fast, reliably, and at scale. This page is all about how Goku's dataset is built and refined. Since generative models rely on massive datasets, curating high-quality data is essential for better image and video generation. If you look at Figure 2, you'll see the entire data curation pipeline. The process starts with raw video and image collection from multiple sources, including public datasets and proprietary datasets. The text-to-image dataset contains 100 million public samples from Leon and 60 million high-quality internal samples, while the text-to-video dataset includes 11 million public clips and 25 million in-house clips. But not all data is useful. So next, the model filters out low-quality or irrelevant content. This includes aesthetic scoring, which prioritizes visually appealing images and videos, motion scoring, ensuring video clips contain meaningful movement rather than static frames, OCR filtering, removing videos overloaded with text, and DINOV2 similarity matching, which helps maintain dataset diversity. And then comes captioning, where videos are tagged with descriptive metadata to ensure the model learns proper associations. Finally, they use data balancing to prevent the model from being biased toward a specific type of content. In short, this page explains why high-quality, well-balanced datasets matter. Without a well-curated dataset, the model could generate repetitive or low-quality results. The Goku team's multi-step curation process ensures diverse, high-quality data, which is essential for better training and performance. On this page, we dive into how videos are processed before being used for training. Since Goku learns from real-world videos, ensuring high quality and consistency is crucial. If you look at Table 3, you'll see the video quality thresholds. Videos must be at least 4 seconds long to ensure they capture enough motion. The resolution must be at least 480 pixels, meaning anything too small gets filtered out. To avoid blocky, low-quality visuals, videos must have a bitrate of at least 500 kilobits per second, ensuring good clarity without excessive file size. Finally, frame rates are standardized to at least 24 FPS, preventing stuttery, unnatural movement. Next, we get into pre-processing and standardization. Internet videos come in all kinds of formats, frame rates, and resolutions, which makes training messy. To fix this, they convert all videos to a standard format, H.264, and apply strict filtering to remove noisy or inconsistent data. Then, we have video clip extraction. The system splits videos into meaningful clips using a two-step approach. First, they apply scene detection, identifying natural transitions. Next, they use a method called DINOV, two similarity matching, to compare adjacent frames. If two frames are too different, it signals a scene change, helping segment the video into logical clips. Finally, we have aesthetic filtering. A model assigns an aesthetic score to each video clip and removes lower quality content. If a clip scores below 4.3 for lower res videos or 4.5 for high res videos, it gets discarded. This ensures that only photorealistic, visually rich videos make it into the dataset. In short, this page explains how Goku ensures high video quality. From duration and bitrate requirements to scene detection and aesthetic scoring, every step is designed to improve training data and enhance generation quality. This page focuses on how video data is filtered, captioned, and balanced before being used for training. If you look at Table 4, you'll see a structured way to categorize video data by resolution: low, 480p, medium, 720p, and high, 1080p. Each category has its own thresholds for visual similarity, aesthetic quality, motion, and text presence. The goal is to ensure that only well-framed, visually rich, and well-structured video clips make it into the dataset. One key filtering step is OCR text filtering. If a video has too much text, measured as a percentage of the screen area covered, it gets removed. Lower resolution videos are allowed a slightly higher text ratio, while high resolution videos must be cleaner. Next, we have motion filtering. Unlike images, videos need motion to be meaningful, but too much or too little can be a problem. To control this, the model computes motion scores using an optical flow algorithm. Videos with almost no motion or extreme motion, e.g., shaky cam, are filtered out. Then comes captioning. For images, captions are generated with intern VL 2.0. For videos, captions are built in 2 steps. First, keyframes are labeled with intern VL 2.0. Then a second model, Tarsier 2, describes video-level motion dynamics. This ensures that captions accurately describe both the scene and movement. The motion score is even embedded into the caption, so the model can learn to generate videos with different motion intensities. Finally, we get to training data balancing. Video models tend to overfit on certain types of content. So to fix this, an automated system classifies videos into semantic categories. The dataset is then balanced across these categories, ensuring a diverse and representative training set. In short, this page explains how Goku's training data is carefully filtered and labeled, ensuring high-quality, well-balanced, and diverse video content. This page dives into how training data is balanced to ensure diverse and fair representation across categories. If you look at Figure 3a, you'll see that nearly half of the dataset is made up of human-related videos. Other major categories include scenery, food, and urban life. However, smaller categories like sports, entertainment, and dance are underrepresented. Since videos containing humans are more visually complex due to varying appearances, clothing, and poses, they present greater modeling challenges. Meanwhile, landscapes and animals are easier to model because they have more consistent appearances. To address this imbalance, Goku's training system downsamples overrepresented subcategories and upsamples underrepresented ones through artificial data generation and oversampling techniques. This ensures that the model gets enough examples of every category without biasing toward common ones. Next, if you look at Figure 3b, you'll see a deeper dive into the subcategories. For human-related videos, the dataset consists mainly of selfie-style clips, half or full-face shots, with some multi-person scenes, crowd footage, and parent-child interactions. For scenery videos, there is a strong focus on natural landscapes like forests, rivers, and mountains, while artificial environments, e.g., roads, cityscapes, are much less represented. In short, this page explains how data balancing ensures a fair and comprehensive training dataset, preventing the model from overfitting on specific video types while maintaining diversity across different subcategories. Let's talk about how Goku Text-2 Image stacks up against other top image generation models. The results are summarized in Table 5, where 3 major benchmarks, Generative, Text-2 Image Comp Bench, and DPG Bench, are used to assess text-to-image alignment and visual quality. First, Generative tests whether an AI model can accurately transform text descriptions into images. Since Goku Text-2 Image is trained on rich, dense captions, it performs well in this task. The researchers also experimented with expanding prompts using ChatGPT-4o, making them more detailed while keeping their original meaning. With these longer prompts, Goku Text-2 Image achieved the best score, 0.76, outperforming models like SD3 and DALL-E 3. Next, Text-2 Image Comp Bench evaluates how well-generated images match their descriptions based on color, shape, and texture accuracy. Here, Goku Text-2 Image consistently scores higher than most models, showing that it can generate visually accurate and well-aligned images from text input. Finally, DPG Bench measures the overall quality of image generation across multiple attributes. Again, Goku Text-2 Image 2B ranks among the top performers with a final score of 83.65. Overall, these results demonstrate that Goku Text-2 Image is highly effective at producing images that align well with text descriptions while maintaining high visual fidelity. Now let's talk about how Goku 2B performs in video generation. This page focuses on zero-shot text-to-video performance using UCF-101, a widely used video dataset. Unlike text-to-image tasks, video generation requires capturing both spatial and temporal consistency. First, they generate detailed captions for all UCF-101 videos using Tarsier-34B, a language model trained for video descriptions. These captions are then used as prompts for Goku 2B to synthesize videos. In total, 13,320 videos are generated at 3 different resolutions: 128 times 128, 240 times 360, and 256 times 256. To measure quality, they use Frechet Video Distance, or FVD, which checks how close generated videos are to real ones, and Inception score, which evaluates their diversity and realism. As shown in Table 6, Goku 2B outperforms many baselines, including models like Make a Video, Emu Video, and SVD. At 128 times 128 resolution, it achieves an FVD of 217.24, significantly better than other models. These results confirm that Goku 2B consistently generates higher quality videos, with better motion consistency and visual clarity than existing models. Let's talk about how Goku T2V stacks up against other video generation models. This page dives into VBench, a comprehensive benchmark for evaluating text-to-video models across multiple attributes. If you look at Table 7, you'll see a detailed comparison between Goku-T2V and models like AnimateDiff-V2, VIDEOCRAFTER 2.0, OpenSora, and Luma. Goku T2V achieves the best overall performance with a score of 84.85, standing out in categories like human action, dynamic movement, and multiple object generation. It also maintains competitive performance in appearance and semantic alignment. Now let's break it down further. Goku T2V is particularly strong in capturing human actions, which is often challenging in generative models due to complex movement and articulation. It also excels at handling multiple objects within a scene while maintaining coherence. These strengths highlight its ability to generate high-quality, diverse video content. The last section touches on image-to-video generation. Goku-T2V was fine-tuned from its T2V model using 4.5 million text-image video triplets, ensuring it generalizes well across different types of content. Even with just 10,000 fine-tuning steps, it efficiently animates reference images while maintaining alignment with the input text. Overall, Goku T2V is pushing the boundaries of text-to-video generation, setting a new benchmark on VBench. Let's talk about how Goku I2V performs when turning still images into dynamic, high-quality video sequences. If you look at Figure 4, you'll see a great visual breakdown. It shows how reference images evolve into motion. The first example features a lion running while flames engulf its body, gradually transforming into fire. The second example highlights a woman lifting weights, capturing her biceps flexing, and sweat forming on her forehead. The last example follows a surfer riding a wave, with the camera tracking his face as he smiles. The model does an impressive job of preserving key details while introducing fluid motion. Now, onto comparisons. The researchers tested Goku-I2V against open-source models like CogVideoX and OpenSora Plan, and commercial tools like Dream Machine and Vidu. They found that commercial models often struggle with complex prompts, failing to generate coherent video elements. Goku-I2V, however, accurately integrates prompt details, producing smooth and consistent motion. The ablation study explores two things: model scaling and joint training. Scaling up from 2B to 8B parameters helps reduce distortions in complex objects. Joint training, where both images and videos are trained together, produces more photorealistic results compared to models trained on video alone. This suggests that combining both modalities enhances video generation quality. Goku-T2V's performance gets a serious boost when you scale it up and apply joint training. If you look at Figure 5, you'll see two key experiments. First, model scaling, the difference between using 2B versus 8B parameters. The larger model creates much sharper, more coherent video frames that capture motion fluidity and object details far better than the smaller version. If you compare the surfer, cyclist, and interaction scenes, you can see how the 8B model produces cleaner and more consistent outputs. Then there's joint training, where the model is trained on both images and videos together. Without joint training, the generated video frames are blurry, unnatural, and sometimes distorted. But with joint training, the results become crisper, photorealistic, and smoother in motion. This highlights the importance of combining both image and video training to improve overall quality. Figure 6 shows how different AI models handle video generation. You'll see side-by-side comparisons of generated videos from several top models. The input prompt describes an underwater drone navigating through a coral reef, with mentions of vibrant marine life, light penetrating the water, and smooth movement through coral arches. The goal? See which model best translates this complex visual scene into a realistic video. Looking at the outputs, some models struggle with motion consistency, color balance, or object distortion. Pika, for example, produces darker, less vibrant visuals. OpenSora Plan seems to capture the overall structure, but has less refined details in the coral. Dream Machine and Xing introduce more dynamic fish movement, but sometimes lose coherence across frames. Then there's Goku, 8B. This model maintains object stability, handles light reflections accurately, and ensures smoother camera motion. The drone and its output moves naturally, without sudden jerks or glitches, keeping the scene realistic. The comparison highlights why fine-tuned training and high-quality data matter. In complex scenes with multiple moving elements, Goku seems to get the balance of detail, consistency, and realism right. To wrap up, Goku is built for joint image and video generation at an industry standard. The model's architecture balances fine-grained data selection and modality integration, creating high-quality outputs that maintain realism. By leveraging a shared latent space and rectified flow, Goku achieves strong token interactions across images and videos, making it highly adaptable for different content types. Thanks for joining us today. Happy learning and stretching together.